The Middle Ages hid a golden age of astronomy right under our noses. Long before telescopes and modern science, medieval scholars cracked cosmic codes with nothing but brass instruments and raw intellect. This video uncovers 25 medieval astronomical discoveries that shockingly predated what we consider modern knowledge. You will leave with a completely new appreciation for this era, seeing the night sky through the eyes of the monks and astronomers who first mapped its deepest secrets. How did a 14th-century scholar in Damascus develop a planetary model that Copernicus would later use? What forgotten instrument acted as a portable computer for navigating the seas? We are about to journey through centuries of celestial observation that built the very foundation of our cosmos. What part of the past do you think we have overlooked the most? A brass disc no larger than your hand held the mathematics of the heavens. This was the astrolabe, a masterpiece of medieval engineering. Imagine a ship's navigator on a moonlit sea, raising this instrument to sight a star. By measuring its angle above the horizon, he could pinpoint his location on the vast, featureless ocean. This was not guesswork, it was precision. Islamic scholars like Al-Biruni in the 11th century perfected its design, transforming it into a portable computer for its age. Its intricate metal plates, etched with star maps and geometric curves, could tell the time, predict sunrise, and even determine the direction to Mecca. The underlying principles revealed a sophisticated grasp of spherical astronomy, the complex science of projecting the dome of the sky onto a flat plane. Centuries later, the English writer Geoffrey Chaucer, better known for his Canterbury Tales, would author a detailed guide on the astrolabe for his young son, proving its enduring role in education and daily life. How did such a device transform society? It shrank the cosmos, making the stars a practical tool for exploration, trade, and prayer. This very act of mapping the sky with such exactness set the stage for an even more daring question. Could the ancient models of the planets themselves be wrong? Inside the quiet scriptorium of a 14th-century Damascus observatory, a scholar named Ibn al-Shatir was quietly dismantling the universe as it was known. His tools were not telescopes but ink, parchment, and a formidable intellect. He focused on a persistent flaw in the ancient Ptolemaic system, a problem called the equant. Ptolemy had used this imaginary point to make his planetary models work, but it violated the cherished principle of uniform circular motion. It was a mathematical cheat. Ibn al-Shatir's genius was to strip it away. He built entirely new geometric models for planets like Mercury and the Moon, models that relied solely on combinations of perfect circles. His intricate diagrams, surviving in detailed manuscripts, did more than just satisfy philosophical purity. They produced predictions for planetary positions that were stunningly accurate, aligning far more closely with what he actually observed in the night sky than anything Ptolemy had offered. This was a monumental shift from blind tradition to evidence-based science, and here is the most astonishing part. Centuries later, when Nicolaus Copernicus developed his sun-centered theory, the mathematical mechanisms he used to describe planetary orbits were nearly identical to those Ibn al-Shatir had devised. This was not a mere coincidence. It points to a vibrant, unseen river of knowledge flowing from the Islamic world into Renaissance Europe. How many other breakthroughs were born in one culture and then credited to another? This mathematical revolution in the mind demanded a new kind of tool for the hand, one that could translate these complex theories into precise measurements under the open sky. While Ibn al-Shatir was rethinking planetary motion, another tool was mastering the art of measurement itself. In the open courtyards of medieval Cordoba, an astronomer would lift a large wooden quadrant, a simple yet profound instrument shaped like a quarter circle. Its curved edge was precisely etched with degrees, and a weighted plumb line hung from its apex. By sighting a star or the sun along one straight edge, the astronomer could read its altitude directly from the scale where the plumb line crossed. This was angular measurement made tangible, and it revolutionized celestial cartography. Figures like the 12th century scholar Jabir ibn Aflaq criticized Ptolemy's astronomical models and championed the quadrant's use, refining the trigonometry that made it so powerful. Its ability to deliver accurate data was not just for star catalogs. It dictated the rhythm of daily life, precisely determining the 5 daily prayer times in Islamic cultures by tracking the sun's journey. The quadrant's true genius lay in its application to spherical geometry. To calculate the exact direction to Mecca, the Qibla, for a new mosque, scholars used this tool to solve complex problems of positioning on a curved earth. It transformed a spiritual obligation into a sophisticated scientific procedure. This very same instrument, in the hands of later European sailors and stargazers, would guide ships across oceans and validate new cosmic theories. Such tools did not merely record the heavens, they gave society the confidence to question the very world beneath their feet. How large was this Earth, and what was its true shape? The question of Earth size was no longer a matter for philosophical debate. In the 11th century, the Persian scholar Al-Biruni stood atop a mountain in what is now India, his astrolabe aimed at the horizon. He was not merely gazing at the view, he was conducting a precise experiment. By measuring the angle of depression from his high vantage point down to the horizon line, he captured a single, crucial data point. He then applied a brilliant trigonometric calculation, using the mountain's known height as one side of a vast, imaginary triangle. The result was a figure for Earth's circumference that came within 1% of the value we accept today. This was not a lucky guess. It was a systematic application of geometry to the physical world, proving medieval scientists could grasp planetary scale with stunning accuracy. His work shattered persistent flat Earth myths and demonstrated that the world was both spherical and quantifiable. What did this mean for the medieval mind? It encouraged a truly global perspective centuries before European explorers set sail. Maps could now be drawn with greater confidence, and the vastness of the world became a known quantity. This profound understanding of our own planet's dimensions demanded an equally precise chart for the heavens above. How did they create a reliable map of the stars without any cameras or computers? A monk's hand moves carefully across a fresh sheet of vellum, tracing the familiar shape of a hunter with a belt of 3 bright stars. He is not creating a new story but preserving an ancient one, copying star charts from Arabic texts that detail constellations like Orion and Ursa Major. This quiet act of scholarship in a European monastery was a vital link in a chain of knowledge that stretched across continents. Far to the east, under the patronage of the Ilkhanate Empire, the Maraghe Observatory buzzed with a more systematic ambition. Led by Nasir al-Din al-Tusi in the 13th century, teams of astronomers compiled exhaustive catalogues. They did not just list stars, they documented their precise positions, their brightness or magnitudes, and their subtle movements across the seasons. These were not simple lists, they were data sets captured in beautifully illuminated manuscripts that were as much works of art as they were scientific instruments. Imagine a traveler, a farmer, or a ship's captain. For them, these star maps were a practical reality. They dictated planting cycles, guided navigation on land and sea, and wove the celestial into the fabric of daily myth and ritual. In 13th century Spain, a different kind of catalogue was born from cultural fusion. The Alfonsine Tables, named for King Alfonso X, synthesized centuries of Islamic and classical Greek observations into a powerful predictive tool. They could forecast the positions of planets for years, even centuries into the future. This systematic recording of the heavens created a stable reference point, a reliable database against which any change or anomaly could be measured. How did these early maps influence both science and culture? They gave the cosmos a fixed address system, allowing future astronomers to notice when something, like a planet, was not where the old tables said it should be. This very precision in mapping the static stars would become the essential backdrop for decoding the restless motion of the planets themselves. The debate was not about whether planets moved, but how they danced. In the halls of medieval Baghdad, scholars pored over complex geometric diagrams, tracing the paths of celestial bodies with a precision that defied their era. They were grappling with a celestial puzzle known as retrograde motion, the apparent backward loop a planet makes against the backdrop of stars. The solution, inherited from Ptolemy but refined to a new level of accuracy, was the epicycle. Picture a planet moving in a small circle, whose center itself travels along a larger circular orbit around the Earth. This elegant, if complex, model created the looping illusion observed from our world. The Persian astronomer Al-Biruni became a master of this system. He did not simply accept Ptolemy's Almagest. He corrected it, recalculating the details of solar and lunar orbits with such painstaking care that his figures were still trusted by navigators and astronomers 5 centuries later. His work was more than just number crunching. It was a testament to a culture that prized observation, where mathematical models had to answer to the hard evidence of the night sky. This relentless drive for accuracy, for a system that truly mirrored the cosmos, sowed the very seeds that would later allow Copernicus to place the sun at the center of it all. What can we learn from these early attempts to decode the solar system? They remind us that scientific revolutions are built not in a single flash of insight, but through generations of incremental, meticulous correction. To track these subtle planetary motions, medieval astronomers needed to master a dimension even more elusive than space. They needed to measure time itself with unerring accuracy. The relentless pursuit of celestial motion demanded a mastery of time itself. Within the stone walls of a 13th-century monastery, a new kind of heartbeat pulsed, powered not by gears of iron but by the steady flow of water. Grand hydraulic clocks, engineered by masters like Al-Jazari, transformed liquid into measured moments. These were not simple timekeepers, they were cosmic simulators. Their dials and automatons did more than mark the hour. They displayed the shifting zodiac, the wandering paths of planets, and the ever-changing face of the moon. Al-Jazari's own castle clock stood as a marvel, a towering assembly of gears, floats, and levers that acted as an early planetarium for its age. It automated the call to prayer and aligned the rhythms of daily work with the grand cycles of the heavens. This was a profound integration of mechanics and astronomy, where art, science, and faith converged to make the abstract passage of time a tangible, visible spectacle. How did such inventions shape our interaction with the natural world? They wove the cosmic and the earthly into a single, predictable fabric, giving society the confidence that the universe operated by knowable rules. This precise, mechanical tracking of celestial cycles provided the essential foundation for the ultimate test of astronomical prediction, the sudden and terrifying disappearance of the sun or moon. A shadow was about to fall across the land, and the astronomers knew it was coming. The prediction of solar and lunar eclipses stands as one of the most public and powerful tests of medieval astronomical skill. In observatories from Baghdad to Oxford, scholars pored over centuries of data, hunting for the rhythmic patterns that govern these terrifying celestial events. They knew that eclipses did not occur randomly but followed a grand celestial clock known as the Saros cycle. This is a period of approximately 18 years and 11 days after which the Sun, Moon, and Earth return to nearly the same relative geometry, and a similar eclipse occurs. By tracking these cycles, astronomers could look deep into the future. The 10th century Persian scholar Abu al-Wafa Bazjani refined these predictions to a new level. He applied sophisticated trigonometric functions to calculate not just if an eclipse would happen, but exactly when it would begin and end, and from which parts of the world it would be visible. This was not abstract math. For European monks, these forecasts were essential for maintaining the complex liturgical calendar, ensuring religious observances fell on the correct days. In the Islamic world, these precise timings were published in comprehensive Zijj, or astronomical tables, which became vital references for timekeeping and navigation. The ability to announce an eclipse before it happened was a profound demonstration of power. It transformed a source of primal fear into a predictable, manageable phenomenon, proving that the heavens operated by knowable laws, not the whims of angry gods. What does this reveal about the practical applications of medieval astronomy? It shows a science deeply woven into the fabric of society, governing time, faith, and even dispelling superstition. This predictive prowess, born from complex cyclical calculations, demanded a new kind of tool to bring mathematical theory down to the observational level. A complex brass assembly of pivoting rings and finely engraved plates sat on the observer's table, an instrument known as the Torquetum. It was a medieval super tool designed to solve a fundamental problem in astronomy. The sky can be measured using different maps or coordinate systems. A star's position relative to the horizon is useful for a navigator, but its location along the path of the ecliptic is what a planet watcher needs. Manually converting between these systems was a laborious task of complex spherical trigonometry. The Torquetum automated this math by carefully aligning its tiers to match the Earth's tilt and turning its dials. An astronomer could directly read a star's coordinates in the horizontal, equatorial, and ecliptic systems without a single written calculation. This was not a tool for beginners. Its very complexity points to a highly sophisticated user, someone engaged in the precise work of correcting star catalogs or refining planetary models. Think of it as a physical bridge, translating the practical sky seen by an astrolabe user into the theoretical sky required for advanced cosmological diagrams. How did such devices enhance the accuracy of medieval observations? They eliminated a major source of human error, turning a night of tedious computation into a session of direct data collection. This mechanical precision in mapping the fixed stars revealed something unsettling. The entire cosmic backdrop was not so fixed after all. The coordinate grids themselves were slowly, imperceptibly drifting. The celestial backdrop, once thought eternally fixed, was caught in a slow, majestic drift. Medieval astronomers, comparing their own star charts with those copied from antiquity, noticed something profoundly unsettling. The bright star marking the first day of spring was no longer where the ancient Greeks had placed it. The equinoxes, the 2 points where the sun crosses the celestial equator, were creeping backward along the ecliptic path through the zodiac constellations. This was the precession of the equinoxes, a wobble in Earth's axis that completes one full cycle every 26,000 years. It was a motion so slow that a single human lifetime could barely perceive its effect. Yet by compiling observations across centuries, scholars like the 13th century Persian astronomer Nasir al-Din al-Tusi calculated its rate with remarkable accuracy. He built upon the foundational work of the ancient Greek Hipparchus, but his own meticulous measurements refined the value, acknowledging that the entire framework of the stars was in gradual motion. This was a revolutionary concept, a cosmos in constant, if imperceptible, flux. For timekeeping and astrology, this drift had immediate practical consequences. It meant that the zodiac sign the sun occupied on the first day of spring was slowly changing, a fact that required careful adjustments to calendars and celestial maps. This long-term perspective demanded a scientific patience we can scarcely imagine today, a commitment to data collection that would only benefit generations far in the future. When Al-Tusi's data eventually reached Europe, it provided a powerful piece of evidence against a static, unchanging universe, nudging cosmology toward a more dynamic model. How did this grand, slow dance of the axis influence the study of a much closer and faster-moving celestial body, our own moon? The moon's path was a riddle of shifting speed and wandering light. While the stars provided a steady backdrop, our closest celestial neighbor refused to follow a simple, uniform circle. Medieval astronomers meticulously tracked its journey, and in the 14th century, a Jewish scholar named Levi ben Gershon confronted its irregularities head-on. He identified specific anomalies such as the evection, which is a slight speeding up or slowing down of the moon caused by the sun's gravitational pull, and the variation, a smaller wobble in its orbit. Ben Gershon did not just note these quirks, he built new geometric models to account for them, using intricate combinations of circles that more closely matched the observational data he and his predecessors had collected. This was not merely philosophical speculation, it was a data-driven correction to a flawed cosmic map. His resulting lunar tables were a leap forward in practical science, offering sailors more precise ways to calculate longitude at sea and allowing astronomers to predict eclipses with newfound accuracy. This intense focus on a single celestial body reveals a profound truth about medieval science. It was not content with grand, universal theories that were slightly wrong. It sought to understand each component of the cosmos on its own complex terms, piece by intricate piece. How did these lunar insights contribute to a broader understanding? They proved that the heavens were governed by precise, if complex, physical laws that could be decoded through patient observation and mathematical ingenuity, setting a powerful precedent for turning attention toward the other wanderers in the night sky. A planet's slow dance against the stars could take years to reveal its secrets, but a close encounter between two worlds offered a moment of truth. Medieval astronomers across Europe and the Islamic world kept watch for these celestial meetings, known as conjunctions and oppositions. When Jupiter and Saturn drew close in the night sky, it was not just a spectacle, it was a critical test. Scholars like Johannes de Sacrobosco meticulously recorded the exact timing and position of these events, using them to poke and prod at their geometric models of the solar system. His text De Sphera became a foundational university textbook for centuries, teaching students how to predict future planetary positions by understanding these cyclical encounters. The detailed diagrams accompanying these records were more than just illustrations. They were data visualizations, allowing astronomers to compare their predicted paths with the actual, observed positions. A noted conjunction of Jupiter and Saturn was not merely an astrological portent. It was a benchmark, a way to verify the complex computational methods laid out in the Alfonsine Tables and other astronomical handbooks. This relentless, systematic collection of data, event by event and year by year, fostered a culture of empirical validation. It was a quiet, persistent form of inquiry that prized evidence over tradition. What can these early records tell us about the persistence of scientific inquiry? They reveal a discipline built on patience, where a single night's observation could confirm or dismantle a theory that had stood for 100 years. This planetary focus, demanding ever more precise measurements of the sky, naturally depended on the instruments that made such exact observations possible. A delicate cage of brass rings gleamed in the candlelight of a medieval library, a miniature cosmos held in a scholar's hands. This was the Armillary Sphere, a three-dimensional map of the heavens where every celestial circle, from the equator to the ecliptic, was represented by a movable ring. More than a simple diagram, it was a dynamic teaching tool and a sophisticated computational device. Medieval craftsmen, building on ancient Greek designs, refined its construction to a stunning degree of precision. A student could physically rotate the rings to simulate the daily spin of the stars, the sun's annual path through the zodiac, or the wandering course of a planet. At institutions like the University of Paris, this hands-on manipulation was central to the curriculum. It transformed the abstract geometry of Ptolemaic astronomy into something that could be seen and touched, making complex concepts like the precession of the equinoxes intuitively understandable. How did such models shape the medieval mind? They encouraged a deep physical engagement with cosmic mechanics, fostering a generation of thinkers who saw the universe as an intricate, knowable machine. This tangible grasp of celestial motion did not stay confined to the library. The very principles embodied in the Armillary Sphere, the understanding of a spherical Earth enveloped by rotating celestial spheres, became the foundational knowledge that guided explorers across uncharted oceans. A Viking navigator stands on the deck of his longship, the cold spray of the North Atlantic stinging his face as he stares not at a featureless sea, but at a fixed point in the heavens. The pole star was his celestial anchor, a constant guide in a shifting world. He raised a simple wooden board, a bearing dial, its edge aligned with the horizon and a sighting pin aimed at that unwavering star. The angle he measured was his latitude. This was not magic. It was applied astronomy, allowing him to hold a course for days across open ocean, from Norway to Iceland, and even to the shores of a new world they called Vinland. This knowledge was meticulously preserved in the Icelandic sagas, epic stories that doubled as navigational logs. Far from the northern seas, Arab traders in the vast deserts of the Middle East employed the very same principle. By measuring the altitude of different stars with their astrolabes, they could traverse the trackless sands and navigate the Indian Ocean, their celestial techniques forming an invisible thread in a web of global trade. This shared method highlights a profound truth. Scientific understanding did not develop in isolation. It was propelled by the very human needs for exploration, trade, and connection. The ability to find your way using the stars transformed astronomy from a philosophical pursuit into a practical tool that shrank the world. This relentless drive for precise positioning, for knowing exactly where you are on the globe, demanded an equally precise answer to another fundamental question. When exactly are you there? The rhythmic chimes of a monumental clock echoed through the town square, a sound marking more than just the hour. In the 14th century, towers across Europe began to host these mechanical marvels, like the one in Prague, whose intricate faces displayed a moving model of the universe itself. Driven by complex systems of interlocking gears and weights, these clocks did far more than tell time. They showed the sun gliding through the zodiac, the moon cycling through its phases, and the steady procession of stars. The Wells Cathedral clock in England included mechanisms specifically designed to track the moon's changing face and even predict eclipses, serving as both a precise scientific instrument and a beloved public spectacle. For the townspeople gazing up, this was not an abstract theory. It was a daily visual lesson in cosmic order, a grand celestial dance made tangible through human ingenuity. How did these clocks shape public understanding of the heavens? They democratized astronomy, pulling it down from the scholar's tower and weaving it into the fabric of community life, where art and engineering united to explain the cosmos. This very fusion of celestial observation with daily human affairs found its most personal expression in the widespread practice of astrology, a discipline that drove much of the period's most meticulous stargazing. A physician unrolls a parchment chart, his eyes tracing the moon's position through the houses of the zodiac. His patient's treatment, perhaps a routine bloodletting, would be scheduled not for convenience but for a specific celestial alignment. This was astrological medicine, a practice where the human body was seen as a microcosm of the universe, its humors ebbing and flowing with the tides of the planets. The moon governing fluids was of paramount importance. A procedure might be delayed for days until the moon left a sign believed to govern a particular limb, all in the hope of ensuring a successful outcome. While its foundations were rooted in a cosmology we no longer accept, this practice had a profound and unintended consequence. It demanded meticulous, long-term observation of the heavens. Monastic healers and scholars like Hildegard of Bingen wrote extensively on the connections between celestial bodies and human physiology, blending their theoretical speculations with careful empirical notes on both the sky and a patient's symptoms. Herbalists consulted lunar calendars to determine the optimal night for harvesting certain plants, believing the moon's light imbued them with greater potency. This created a vast, decentralized network of observers, all watching the sky for reasons of health rather than pure science. The detailed records they kept, noting the moon's phase and the planet's positions alongside medical outcomes, accumulated into a valuable database. Later astronomers, sifting through these old almanacs, could extract precise lunar data that had been recorded for centuries. This intersection of astronomy and medicine reveals a crucial stepping stone in the history of science. It was a context that made celestial observation a matter of life and death, fostering a disciplined habit of looking up and writing down that would eventually shed its astrological skin. How many other scientific disciplines began as practical, even superstitious, arts before their underlying principles were fully understood? This daily monitoring of the moon's phases for health paved the way for a much deeper investigation into the very substance of the cosmos itself. A darkened chamber became a cosmic theater, its single pinpoint of light casting a shimmering image of the sun upon the far wall. This was the Camera Obscura, a revolutionary tool for solar observation. By the 11th century, the brilliant scholar Ibn al-Haytham, known in the West as Al-Hazan, had meticulously described its optical principles, understanding how light travels in straight lines to project an inverted yet perfectly detailed picture. For astronomers, this was a revelation. They could now study the sun safely, watching in real time as dark blemishes, sunspots, drifted across its brilliant face. They could witness the moon's shadow creep during a solar eclipse without a single moment of blinding glare. This was not passive watching, it was active, safe data collection. In European monasteries, monks used this technique to document the sun's behavior over years, sometimes linking prolonged periods of few sunspots to colder winters and poor harvests, an early attempt at connecting solar activity to earthly climate. The Camera Obscura did more than just protect their eyesight. It transformed the sun from an unreachable, blinding orb into a dynamic, physical object that could be measured and analyzed. How did such a simple tool expand the boundaries of observable astronomy? It proved that the most profound discoveries could come from creatively bending light itself, turning an entire room into a scientific instrument. This newfound ability to scrutinize the sun with such clarity inevitably cast a critical light on the established cosmic order, inviting challenges to the theories that had ruled for 1,000 years. A quiet rebellion was brewing in the lecture halls of 14th century Paris. Here, scholars like Jean Buridan and Nicole Orsme looked at the complex clockwork of Ptolemy's universe and found it wanting. They were not satisfied with the mathematical fudges like the equant point that made the old models work. Planetary positions predicted by the Alfonsine Tables sometimes drifted from what they actually saw in the sky, and these inconsistencies became the fuel for a profound intellectual shift. Their critique was not yet a new system but a powerful exercise in doubt. They asked a question that would echo for centuries. If the heavens are a perfect, unchanging realm, why do our best models require such obvious imperfections to function? Buridan, using logical arguments, revived the ancient idea of impetus to explain why projectiles move, challenging Aristotelian physics that had reigned for over 1,000 years. His student Nicole Orsme went even further. In his groundbreaking work Livre du Ciel et du Monde, he presented a detailed argument for the possibility of a rotating Earth. He used everyday analogies, suggesting that if you were on a moving ship, you would perceive the shore as moving, just as we might perceive the stars as rotating around a stationary Earth. He concluded that no observational experiment could definitively prove which one was truly moving. This was a staggering leap of thought, a direct challenge to the geocentric bedrock of medieval cosmology. These scholars were not yet ready to cast the Earth from the center of the cosmos, but their intellectual courage demonstrated that the universe was a place open to rational debate, not blind dogma. What does this tell us about the evolution of scientific thought? True progress often begins not with a new answer, but with the courage to question an old one. This critical spirit, flourishing in the heart of Europe, was itself nourished by a vast and intricate web of knowledge that stretched across the known world. A quiet revolution was taking place not in an observatory but in a scriptorium. In the 12th century, the Spanish city of Toledo became a global hub of knowledge, where Christian, Jewish, and Muslim scholars worked side by side. Their task was monumental: to translate the vast libraries of Arabic and Greek scientific texts into Latin, the language of European learning. Works like Ptolemy's Almagest, which had been preserved and expanded upon for centuries in the Islamic world, were saved from the brink of oblivion and given a new life. At the heart of this movement was a figure like Gerard of Cremona, an Italian scholar who traveled to Toledo specifically to access these treasures. He spent decades translating dozens of foundational texts, introducing European scholars to advanced star catalogues, planetary theories, and sophisticated mathematics they had never before encountered. These were not simple word-for-word copies. The translators actively synthesized knowledge, creating new tools like the Tolden Tables, which blended fresh Islamic observations with the classical Greek framework. Suddenly, a student in Paris or Oxford could access 1,000 years of accumulated celestial wisdom, from ancient Alexandria to medieval Baghdad. How did these translations shape the trajectory of European astronomy? They provided the essential raw material, the data, and the theories that would fuel the scientific revolution. This collaborative legacy proves that science thrives not in isolation, but at the crossroads of cultures where diverse minds can share and build upon a common foundation of discovery. A farmer in 10th century England would have known the precise week to sow his winter wheat by watching for the first pre-dawn appearance of the Pleiades star cluster. This heliacal rising, when a star becomes visible just before the sun after a period of being hidden, was a celestial alarm clock for civilizations across the globe. Medieval societies did not separate astronomy from agriculture. Their survival depended on it. Works like the Byzantine Geoponica compiled this hard-won knowledge, detailing how the position of Orion or the bright star Sirius dictated the timing for pruning vines, harvesting grains, and storing food for the winter. This was not mere folklore. It was a sophisticated, long-term data set built on generations of observing the subtle dance between the constellations and the seasons. The farmer watching the Pleiades knew that their appearance in the eastern sky coincided with the cooling autumn air and the first rains, the perfect conditions for seeds to take root. He was consulting a living almanac written in the stars, a system that optimized food production and managed community resources with a gentle, sustainable rhythm. What can these ancient practices teach us about our own relationship with the environment? They reveal a world where human life was consciously synchronized with cosmic cycles, fostering a deep, empirical connection to the natural world. This earthly wisdom, born from looking up, was soon complemented by a new generation of instruments that brought the sky down to the surveyor and the architect. A simple wooden staff marked with degrees became the sailor's most trusted companion on an empty sea. The cross-staff, a 14th century innovation, was a marvel of practical geometry. A navigator would hold the long staff to his eye, then slide the crosspiece back and forth until its top edge seemed to touch a guiding star and its bottom edge lined up perfectly with the horizon. The angle read directly from the staff gave him his latitude, his north-south position on the globe. This was celestial navigation stripped to its bare essentials, requiring no complex mathematics or expensive brass instruments. Its brilliance lay in its directness. By the 15th century, Portuguese explorers venturing down the African coast and into the Atlantic relied on this very tool. Their voyages of discovery built upon a foundation of medieval ingenuity. The cross-staff did more than just guide ships. It generated a constant stream of angular data, measurements that slowly refined the maps of both the Earth and the sky. Each sailor, with his simple staff, was an unwitting data point in a vast, collaborative project to chart the world. How did this accumulation of precise measurements do more than just guide ships? It provided the raw observational evidence that would eventually force a reconsideration of the entire cosmic structure, proving that the most profound shifts in understanding often begin with the simplest of tools. Could God have placed life on other worlds far beyond our own sun? This was not a question for science fiction, but a serious debate in the medieval university. Scholars like William of Ockham applied his famous principle of parsimony, often called Occam's razor, to the cosmos itself. If God is all-powerful and the universe is vast, why would he create only one inhabited world? This line of reasoning was not based on telescopes or data, but on pure logic and theological possibility. It directly challenged the anthropocentric view that humanity was the sole focus of a divine creation, pushing the boundaries of thought to encompass a potentially infinite cosmos. Nicole Orsme took this speculation even further, contemplating the nature of infinite space and the possibility of other Earths existing in a void. These were radical ideas rooted in metaphysics, yet they fostered an intellectual open-mindedness that was crucial for future discovery. How does such abstract philosophy relate to science? It creates a fertile ground for new questions. By daring to suggest that the universe might be filled with a plurality of worlds, these thinkers were engaging in a form of early astrobiology, using reason to explore the ultimate limits of life itself. Their speculative courage reveals that the medieval mind was capable of breathtaking cosmic wonder, proving that astronomy was as much about asking grand questions as it was about tracking planets. This philosophical expansion of the possible demanded a corresponding precision in the mathematical language used to describe it all. A celestial problem demanded a new mathematical language. The challenge was mapping a curved sky onto flat parchment, translating the dome of stars into precise numbers for calculation. At the Maraghay Observatory, Nasir al-Din al-Tusi and his colleagues confronted this directly, forging the tools of spherical trigonometry. They were not merely calculating, they were building a new grammar for the cosmos, one that could accurately describe arcs and angles on the immense sphere of the heavens. A navigator using an astrolabe needed to convert a star's altitude above his local horizon into its position on the universal ecliptic grid. Doing this manually was a labyrinth of complex geometry, but the mathematical laws these scholars developed streamlined the entire process. The sine law, a cornerstone of their work, established a clear relationship between the sides and angles of spherical triangles, turning a night of tedious computation into a series of straightforward steps. This was the engine behind the precision of the Zij tables, enabling astronomers to predict planetary positions and eclipse timings with a reliability that felt almost prophetic. One of al-Tusi's most elegant innovations was the Tusi couple, a mathematical device that used one circle rolling inside another to generate perfectly straight-line motion from two circular movements. This clever geometric trick provided a powerful new way to model the complex, looping paths of planets without violating the philosophical demand for uniform circular motion. When Copernicus later wrestled with how to make the Earth itself move in his new system, he employed a mathematical mechanism that was functionally identical to the Tusi couple. How did these abstract formulas unlock new celestial insights? They gave astronomers the computational power to move beyond rough sketches of the universe and toward a precise, predictive science. This mathematical revolution did not remain locked in theoretical texts. Its true power was realized when it was compiled into the practical, all-in-one reference books that guided every aspect of celestial inquiry. An astronomer in 14th century Cairo unrolls a heavy parchment, his finger tracing columns of numbers that predict the future position of Mars. This is a Zij, a comprehensive astronomical handbook that condensed a lifetime of observation into a single, usable reference. These tables were the supercomputers of their age, vast databases that catalogued everything from the mean motion of Saturn to the precise timing of lunar eclipses for decades to come. Produced from Cordoba to Samarkand, Zij were not the work of a single mind but of entire observatories, synthesizing Greek, Persian, and Indian data into a unified celestial forecast. Nasir al-Din al-Tusi's Zij-i-Ilkhani stands as a monumental example, compiled at the Maraghay Observatory by integrating fresh observations with refined theoretical models. It did not just list numbers, it provided the instructions, the algorithms for calculating everything from prayer times to horoscopes, setting a new standard for accuracy that would influence scholars for generations. Their true power was their longevity. The Alfonsine Tables, created in 13th century Spain, were still being used by European navigators and calendar reformers in the age of Columbus, their predictive algorithms guiding ships across the Atlantic and recalibrating the very measurement of the year. What can these ancient data sets teach us? They reveal that the backbone of astronomy has always been organized, accessible information. This systematic compilation of knowledge, where thousands of individual observations were distilled into reliable, testable predictions, represents one of the highest achievements of medieval scientific collaboration. It was a global project built over centuries that turned the chaotic dance of the heavens into an orderly, predictable clockwork. This legacy of meticulous record-keeping and cross-cultural synthesis invites a final, overarching question about the true impact of these 25 discoveries on our modern world. A great observatory was more than just a building. It was a scientific ecosystem, a humming center where minds and instruments worked in concert under the patronage of enlightened rulers. In the 15th century, the Samarkand Observatory, founded by the Timurid prince Ulugh Beg, rose to become one of the most advanced research institutions in the world. He was a scientist king who personally participated in the work, attracting the finest astronomers and mathematicians to his court. At its heart was a colossal meridian arc, a fixed sextant sunk into the Earth with a radius of over 100 feet, allowing for unprecedented precision in measuring the altitudes of stars. This was not a lone scholar with a quadrant. This was a team effort, a coordinated enterprise dedicated to systematic data collection over many years. The result was the Zij-i-Sultani, a star catalogue that detailed the positions of 1,018 stars with a level of accuracy that would not be surpassed for another 2 centuries. This collaborative environment, mirrored earlier at the Marrakech Observatory under Nasir al-Din al-Tusi, created a powerful legacy. It proved that monumental scientific progress requires sustained investment, institutional support, and the free exchange of ideas among a diverse community of thinkers. How did these centers pave the way for modern research institutions? They established the very blueprint, demonstrating that gathering brilliant minds with the best tools in a dedicated space accelerates discovery in ways a solitary genius never could. The 25 discoveries we have explored, from the astrolabe to the Tusi couple, from precession to planetary models, were not isolated flashes of insight. They were the fruits of this institutional culture, a testament to a global medieval quest for knowledge that connected Damascus to Paris and Samarkand to Oxford. Their enduring impact is all around us, woven into the fabric of our navigation systems, our understanding of celestial mechanics, and our very conception of a knowable, rational universe. They remind us that the light of science has been carried forward by countless hands across the centuries, each one adding a vital piece to the magnificent puzzle of the cosmos. A bustling library in 10th century Baghdad housed a symphony of languages, where Christian scribes copied Greek texts into Arabic, while Jewish scholars debated planetary motion with their Muslim counterparts. This was the House of Wisdom, a testament to an era where science transcended creed. Caliphs and kings invested vast resources not for mere prestige, but out of a genuine conviction that understanding the cosmos was a noble pursuit that benefited all humanity. The Quran's injunction to reflect on the heavens provided a powerful spiritual impetus for Islamic scholars, driving them to perfect star catalogues and timekeeping instruments. Yet their work seamlessly integrated the astronomical legacies of Greece, India, and Persia, creating a new, unified body of knowledge. This was not a solitary endeavor. From the translation movements in Toledo to the observatories of Samarkand, these cross-cultural collaborations were the engine of progress. Astronomy was not locked in an ivory tower. It was woven into the very fabric of society, determining the correct times for prayer, guiding legal decisions about inheritance based on lunar months, and educating children in the fundamental principles of a spherical cosmos. This rich, interconnected ecosystem reminds us that the greatest leaps in human understanding rarely occur in isolation. They blossom where diverse minds are free to gather, debate, and build upon a shared foundation of curiosity. What hidden potential for discovery lies dormant in our own world, waiting only for the right conditions of openness and exchange to bring it to life? These 25 discoveries weave a brilliant tapestry of innovation, revealing a medieval world alive with cosmic curiosity. The astrolabe's intricate brass plates, the precision of the quadrant, the mathematical elegance of the Tusi couple, each one stands as a testament to an era that was not dark, but illuminated by the light of inquiry. Scholars from Damascus to Paris, from Cordoba to Samarkand, were not merely preserving ancient knowledge. They were building upon it, correcting it, and laying the very foundation for the scientific revolution we so often credit to later centuries. Their work reminds us that progress is a collaborative, cross-cultural journey, a slow and patient accumulation of insight across generations. The next time you look up at the stars, think of the medieval astronomers who first mapped those wandering lights with nothing but their intellect, their dedication, and a handful of beautifully crafted tools. Their legacy is written in the very way we understand our place in the universe today. I would love to hear which of these discoveries amazed you the most. Was it the predictive power of the eclipse calculators or the sheer ingenuity of the portable astrolabe? Share your thoughts in the comments below, and if you enjoyed this journey through history's hidden gems, please subscribe for more. Together, let's keep exploring the stars, honoring the legacy of those who first charted their mysterious path.